In this video, we're going to talk about how do we find probability of the complement of an event. Let's do this with an example. Let's say we toss a coin 3 times and we define an event A such that happens when 3 of a kind occurs. So we need to find the probability of A not happening. Basically, we need to find the probability of the complement of A. Pause the video, think about it. Okay, let's do this. Let's figure out the sample space. We have 8 equally likely events. And let's see, where do we have 3 of a kind? Well, 3 of a kind means we'll get the same thing on all 3 coins. So we have this one, all 3 of them tails. And then we have this one, all 3 of them heads. And that's it. So we have 2 out of 8 events where we have 3 of a kind. So the probability of A happening will be 2 by 8. And the probability of A not happening, which is the complement of A, that's going to be the remaining 6 events, that's going to be 6 by 8. Let's write that down. Probability of A is 2 by 8. Probability of A dash is 6 by 8. Another way to find the probability of complement of A will be to subtract the probability of A from 1. We can do this. We can say that 6 by 8 is also equal to 1 minus 2 by 8. In general, probability of A dash is always equal to 1 minus probability of A. And this seems intuitive, but we're going to prove this using our axioms. So let's do this. This is our sample space and this is A. And if this is A, the rest of it, which means everything outside of it, will be A dash. So this is A and this is going to be A dash. Alright. So already you can see that A and A dash are mutually exclusive. By definition, there is nothing in common. So A and A dash are mutually exclusive. And we also know that they are exhaustive because both of them teamwork to cover the entire sample space. So A and A dash are also exhaustive. Because they're mutually exclusive, we can say that there's nothing in common. A intersection A dash is phi. And because they're exhaustive, we can say that the union of them is the entire sample space. A union A dash is equal to the sample space. Let's find the probability of this second one, probability of A union A dash. Well, that's going to be equal to probability of sample space. And by axiom 2, we know that the probability of sample space is 1. So by axiom 2, probability of A union A dash, that's going to be 1. And because A and A dash are mutually exclusive, there's nothing in common, we can split this up and say that this is equal to the sum of their individual probabilities. By axiom 3, we can say that this is equal to probability of A plus probability of A dash. And a little rearranging will give us probability of A dash equals 1 minus probability of A. So we have proved this using our axioms. Let's quickly solve a few problems. Okay, this is the first one. Probability of A is 2 by 9. What is the probability of A not happening? Which means probability of A dash. And we can do this mentally. We can subtract this from 1. 1 minus 2 by 9, that's 7 by 9. So probability of A dash is 7 by 9. Let's do one more. If a letter is chosen at random from the word assassination, find the probability that the letter is a vowel and the probability that the letter is a consonant. Just a quick note, vowels are A, E, I, O and U. So what's the answer? Well, let's break this down. Assassination. Let's count the number of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So out of these 13 letters, how many vowels do we have? Well, the green ones are vowels. 1, 2, 3, 4, 5 and 6. Okay, so the probability of getting a vowel is 6 by 13. And to get the next one, either we can count the number of consonants or we can subtract this probability from 1. Let's do that. Probability of consonant is 1 minus 6 by 13, that's 7 by 13. These two are complements of each other and that's what we're using here.